Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem, two keys keyboard. The idea with this problem is we start out with a single character, and that is A, though the character doesn't really matter in this case, but we have two operations that we can do. We can either copy all of the characters here, which initially is just a single A. The second operation is pasting all of the characters that we have copied. So initially, you can say that our clipboard, the area that contains the characters that we have currently copied, is empty. So initially, there's nothing that we have copied. The first choice that we have to make is copying all of the current characters, which is just a single A. So at that point, just kind of drawing out the tree, we could paste a single A, which would give us two A's, and that's really all we can do. I mean, we could repeatedly keep copying the character, but that's not really going to do anything. So this is like the only possible state. Like this is a state that we have to get to eventually. Here, though, it becomes more interesting. Here, we could decide to paste another A, which is already in the clipboard, so then we'd have three, or we could copy all of these and then paste them again, which would give us four A's. So then at this point, we could add two more A's, which would give us six A's. I'll just kind of draw it like this. Or we could copy everything here and then paste them again, which would give us eight A's. One thing to notice is that the size of our clipboard, the number of A's that we have currently copied, is never going to decrease. Like initially we have one A copied into the clipboard. We can paste it and then paste it again and keep pasting it. But as soon as we copy like the current selection, which could be two A's, or it could be three A's, or it could be four A's, we can never decrease the number of A's that we have copied. And so what we're ultimately trying to do here is we're given some number n, that's the only parameter given to us, and we want to know what's the minimum number of moves it would take for us to have exactly n A characters. And it's always going to be possible to form this because remember, we initially start with one A and we can copy that A, so then we can just paste it however many times we need to reach that target. So it's always going to be possible, but we want to know what's the minimum number of moves to reach that. And so remember that copying counts as a move and pasting counts as a move as well. So the brute force is not super complicated. We keep track of two things. We keep track of how many A's we have, like I'll call that the count, but there's probably a better name for it. And also however many that we have currently in our clipboard. We could call that cur or paste or whatever, but however many A's we have currently. So initially, we know that the count starts at 1. We have one A available and our clipboard starts at 0. But we know that the first move has to be copying this. So I guess we could set this to 1 and also just keep track of that like as the number of moves that we've already made. So then there's a couple choices. We could paste, which would get us to 2A, so that would cost one move to paste, and it would increase the count by whatever that happens to be. So it would be basically count plus however many are currently in the clipboard, and then paste would stay the same. So this would be that new state. Now the other choice is, well, it doesn't really make any sense when we start here, but the other choice would be to copy, to not just paste, but to actually copy. Well, initially we've already done that here, so let's kind of make that decision down here. We could copy what we currently have here and also paste it because we don't want to infinitely get stuck in just making a copy because we could copy what we have here and then that would bring us to where we already are. But now our clipboard will have two A's and then we could keep just making that decision repeatedly. So we don't want to get stuck in this sort of like infinite recursion. So whenever we make a copy operation, we're also going to paste. So this will cost us two moves, but we will get to this, four A's. So the way that would update our count and our paste would be whatever our count happens to be is what our paste is going to be replaced with. So that's what this would be here. But also the count is going to double because if we take what we already have, copy it, and then paste it, well, we basically just doubled this. So you could have this multiplied by 2. So this is a very classical sort of backtracking solution. And given that we only have two variables here, we can apply caching to this. So this can be optimized with memoization. So I'm going to go down the dynamic programming path of solving this problem. I think the rest will probably make more sense when we actually code it up, but I do encourage you to try to draw out the decision tree. It's a little bit interesting for this problem, which is why I didn't want to like draw out the whole thing. I think just thinking in terms of these variables is the simplest approach. So I'll also analyze the time complexity when we actually code this. So I'm going to have a helper function, which is going to keep track of the two things I was talking about, the count and the paste. I know there's definitely some better variable names for this, but this is just going to keep track of how many total A's that we have, and this is going to keep track of how many we can currently paste, so how many are in the clipboard. Before we even implement this, this helper function is going to be called like this. We're going to initially start with 1A, we always do, and we're always going to start with 1 in the clipboard because we have to do it this way. So to offset the fact that we had to do one operation to fill the clipboard, I'm going to have a +1 here. So whatever this returns, +1, because this helper function will tell us how many operations it's going to take before our current count reaches n. For the base case, the simplest one, of course, is when the count is directly equal to n. So at that point, there's no more operations needed, so what we can do is return 0. The other case is where the count becomes greater than n. So at that point, in Python, the easiest thing to do is return infinity, so some really large number. But when this gets called, we might add to it. So in most languages, that would overflow this number. We don't have to worry about that in Python, but still a better way to code this up would be to use a really large number where we know we're never going to hit that number, but at the same time, it's not going to overflow. Based on the constraints of this problem, they give us n is never going to be greater than or equal to 1,000. So we can confidently say it's not going to take more than 1,000 operations for us to reach that number, because remember, we could just copy a single A and then paste it however many times. So a good default value here would be to just return 1,000. So now in terms of the recursion, remember that we had two main choices. There was pasting and then there was copying. But with copying, we don't just want to copy, we want to copy and paste. These decisions would look something like this. So with pasting, we already have something in our current clipboard, so it's going to take us one operation to do that. So it's going to be 1 plus helper, and then this is going to be the remaining subproblem. If we were to paste right now, it takes us one operation to do that. And what's the remaining subproblem going to be? Well, count tells us how many A's we currently have. So count would be updated to this plus whatever is currently copied. So whatever we end up pasting is going to be this. And our current paste will not change. What we have copied is not going to change. So that would stay like this. So this is going to be the result of pasting. With copying, it's going to be a little bit more interesting. If we were to just copy, that would be pretty simple. That would be like this, where count doesn't change, but our paste now becomes whatever we have copied, which is what our current count happens to be. So that would become this. Now, this is not super interesting because this could go infinitely. Like we could just keep copying and that would update this, but nothing else would be updated. So that could go forever. So we don't want to run into that case. So we change it to be copy and paste, because as soon as we copy, the only thing that we can do after that is paste. There's no point in copying multiple consecutive times. Pasting would then change count to be count times 2 or just count plus count. And obviously this is not going to be one operation, it's going to be two operations, so we put a +2 out here. So now among these two, we want to minimize them and then return the result. So I guess I'll just call this result 1 and call this result 2. And then we'll end up returning the minimum of both of these. But this is not very efficient. This is going to be exponential. So we can fix this by doing some caching. So up here, we will declare a hash map. So now if we see the same subproblem, so we can add a condition here. So if this is in our cache already, go ahead and return cache with these parameters. Whoops, let me add that. And also before we return, let's make sure to cache this. So cache with these parameters is going to be assigned to this, and then that's what we're going to end up returning. So this is pretty much the entire recursive code, unless I have a mistake somewhere. Actually, I definitely do. So one, we want to return this. That's the easy part. But the other thing is, there is actually a case where n could be equal to 1, but we already start with 1a, and that's actually the second example in this problem. So we will actually fail that test case currently because we say 1 plus the result of helper. But if n is equal to 1, then it should take us 0 operations to reach that, since we already start there. So here we can add like an if statement for that. If that's the case, return 0. So now I think we're good. Let's run this. And yep, you can see on the left that it works and it's pretty efficient, but there is a way we can optimize the memory when it comes to dynamic programming. By the way, though, this time complexity, you can see that in here, everything is a constant call other than the recursive calls. And how many different times could they be called? Well, count could be as large as n. Paste could also be as large as n, so the overall time complexity is going to be O of n squared. Space complexity is also going to be that, since that's how many subproblems we could have cached, so this is also going to be n squared. We can optimize this to make it an n squared time solution and an O of n memory solution, and I think it's a solution that is somewhat understandable. There is like a third solution, which relies a lot on like math and prime factors, which we could get the time and space complexity down to this, but I actually will not be covering that solution in this video. I don't think it's a super useful one, to be honest. Now, the next solution I'm going to show you is actually even more simple than the previous one. It just kind of requires slightly different thinking. I guess you could say like sort of a trick, but it's not that complicated. So let me kind of explain this to you. We start at 1. We have just a single a, and our goal is to eventually reach n. At some point, there's going to be the last gap that we fill. Let's say the distance of that gap is x. So that's what we currently have pasted, or like that's currently what we have copied in our clipboard, and that's what we're going to end up pasting. Well, for us to have pasted this, eventually that means we had that and we ended up copying that, right? So you must agree with me on this so far, that this is the last term that we pasted, whatever it happens to be. It's going to at least be like 1. So the minimum number of operations to reach n, assuming x is the last term, the last like paste value we do, it's going to be n divided by x. So how many times does x go into n? And so that is going to tell us how many it would take to go from x all the way to n. So then the entire problem, how many steps did it take to get to n, becomes this, plus how many steps it took to get to x in the first place. So this is very recursive. This is a dynamic programming solution where like that's the subproblem. So let me call that dp of x. So whatever the result of this subproblem is, that's how many steps it takes to get there, plus this is the minimum number of steps it's going to take to get to n, assuming that x is the last term, but x may not necessarily be the last term. The concept of this solution that I'm explaining is actually very, very simple. If it starts to seem complicated here, I would just go to the code, because honestly, the code makes a lot of sense. I just think explaining why this works is worth doing, and that's how you get to this sort of picture here. To kind of review of how we're going to get to n, first, we're obviously going to have to compute that subproblem first, like what's the minimum number of steps it takes to get to x. So that's what we're doing. We know it takes 0 operations to get to 1. So then what's the minimum number of operations it takes to get to 2? Well, that's going to be 2 operations. The way we would calculate that is by doing this, by taking 2 and dividing it by the previous step. So like if we had 1, how many times does 1 go into 2? That's 2. Plus the result of this subproblem. So you'd say dp of 0, or rather of 1, plus this. We know that this is 0 initially, so this becomes 2. By the way, those 2 operations in this case would be copying 1 and then pasting it a single time. More generally, when this term is something like an x, you can say that it took us however many operations to get to x, and then to get to n from here, we're going to have to copy this and then paste it this many times. Technically, this minus 1. But anyways, like this formula tells us the total number of operations to go from x to n, because we would copy this and then paste it however many times we need to get here. Even for x itself, it could be somewhere arbitrarily in the middle. To get to here, there was some other term, call it y, where y had to be pasted however many times. It could have been 2 times, or it could have been more than 2 times. So that's kind of like the recursive nature of this problem. And so doing it this way, we can solve it in a bottom-up fashion just by having one array in memory, where dp of I will tell us the minimum number of operations to get to I. And then to get to n from there, we can just take this I and multiply it however many times we need to. We don't have to necessarily go through every single candidate. So for example, if we have an x here, just for example's sake, let's say 10 here is 100 and x is 12. Well, we know that 12, a multiple of it is never going to be equal to 100. That's because 100 is not divisible by 12. So we could skip 12. We don't need to consider this being multiplied to eventually get here. And also, we know that we don't have to consider any factor of n that is larger than n divided by 2, because n divided by 2 is the biggest factor for this anyway. That number multiplied by 2 would reach here. If we consider anything larger than that, it's never going to be a factor, so we can skip those as well. That's just a kind of a small optimization. So the code that I'm about to show you is going to be n squared in time and O of n in space. Okay, so coding it up, we're going to have our dynamic programming space, which is going to store the result of all the subproblems. So the size of this is going to be n plus 1, so going from 0 all the way to the nth index. Each of these is going to represent the result of the subproblem. So the one that we're going to return is going to be dp of n. That tells us how many moves it takes to get to n, the minimum number of steps to get to n. So the value that we can put here, we're trying to minimize it, so we should probably put a big value. You could put float of infinity. In Python, that will work. In most languages, though, you're going to need to put a real number. So here, let's do 1,000. And the base case that we kind of talked about in the drawing explanation is still the same, where the minimum number of steps to get to 1 is going to be 0. And then we're going to compute the result of every subproblem from 2. So for I in range starting from 2 all the way up until n. So I'm going to put an n plus 1 here. And then to compute the result of dp of I, the minimum number of steps to get here, let's consider every factor up until I divided by 2. So for j in range from 1 all the way up until I divided by 2. And here in Python, this will actually be non-inclusive. So we actually want to execute this iteration. So we're going to do 1 plus this. I don't think you actually need the parentheses here, but I'll do it just to make it more clear. This will start at 1 and go all the way up until I divided by 2. We want to consider this as a factor of I. Let's say this is the last factor of I. So the number of steps to get to I would then be dp of j. This is the factor. So how many steps did it take to get to this factor? And then how many steps would it take to get from j all the way to I? Well, that's just going to be copy and pasting this however many times. So it's basically this plus I divided by j. How many times does j go into I? So this is the number of steps. So to minimize it, we set dp of I equal to the minimum of itself, dp of I, and this that we just computed. But remember, we only want to do it for actual factors of I. So we say if j is a factor of I, that's pretty easy. If this modded by j is equal to 0, then we calculate this formula. So that's the whole thing. It's not super complicated once you realize what we're doing, but it's not obvious, I think, to jump to this solution just because, at least in my opinion, the backtracking recursive solution is easier to come up with, and that's somewhat different from this one. This one, you do have to make a very key observation, which is that eventually there's going to be a factor, like the last factor of I, which is going to be pasted however many times to get to I. So let's run this, and you can see it works, and it's pretty efficient. The memory is definitely more efficient. So if you found this helpful, please like and subscribe, and check out Leetcode.io for a lot more.